Okay, here we are with the exam 3 review in for multivariable calculus, math 234, in summer semester of 2023. And with that preamble out of the way, let's just dive right in there. So, first thing that we want to do in exam 3, our big focus is on multiple levels of integration. So we're going to be looking at integrating stuff with respect to each variable that we're going to toss into our mix, which means we'll be doing a lot of double or triple integrals. However many variables we have, that's the number of integrals we'll do. And the first step that we want to talk about when it comes to what a double or triple integral actually is to fall back to our Riemann sum idea all the way back in Calc 1. In Calc 1, we said that the area underneath the curve could be approximated by making a bunch of rectangles and adding up the area of those rectangles. In double integration, we're going to have a third dimension going on. So we've got our third z variable, which means that instead of looking at the area under a curve, we're going to look at the volume under a surface. And pretty much the same theory is going to apply, where we're going to start by approximating that volume with a series of boxes, and then add up the volume of those boxes and say that that's approximately equal to what we got. And then in a very similar fashion to how we went from Riemann sums to integration in Calc 1, we'll do the same thing here from Riemann boxes to integration, where we just take a couple of limits and magically it turns into an integral. But before we get into the integral part, the integration part, we're going to do at least one example of approximating it with some boxes. So I've taken the liberty of sketching our region already, where our region is the rectangle determined by the inequalities. X is between -1 and +1. Y is in between 2 and 4. And we're going to choose a subdivision of D into squares with a side length of 1. And we're going to use sample points of the Riemann sum at the top left corner of each subdivision to approximate the integral of that function over this here region. Oh, right. And then we have a function value as well, or a function value. We have a function that's defined for us. That's this guy up here. Be our function. And again, we want to go with the top left corner of each square. Yep, I drew my region D. It's that 2 by 2 rectangle. We're going to split it up into squares with a side length of 1. Our D region is already a square with side lengths of 2. So we're going to divide each dimension in half. And we'll end up with 4 squares. Square number 1, square number 2, square number 3, and square number 4. Those are going to be the 4 squares that make up the subdivision of our region. And again, we're going to look at calculating the volume of boxes that have these square bases and a height that's determined by the function value in the top left corner. So within box or square number 1, the top left corner is this blue point. Within square 2, top left corner is going to be the red point. Square 3, the green point. Square 4, the purple point. So I'm going to look at each of those points and calculate the height of the box at that point. And again, that height is going to come from the function value, because our function value is basically z equals some function of x and y. So if I wanted to approximate that volume, it's approximately length times width times height. And we're going to do that for each box. But since the length and the width of each square is identical, the volume could be a little more easily approximated with just length times width times the sum of all of the heights. Because when we add up the volume of the boxes, we could factor length and width out. So from the first square, we're going to need the function evaluated at -1, 3 plus the height of the second box, which is the function evaluated at 0, 3, plus the third box. That's the function at 0, 4. And finally, the fourth box, which is the function at -1, 4. And then from there, it's just a plug and jug. Our length and width are both 1 because we've got squares with side length of 1. And then we just plug our points into the function. So x times 1 plus y. So for that first spot, we'll have -1 times 3, which is -4, plus the red spot, we'll have 0 times 4, which is 0, plus the green spot, 0 times 5 is also 0, plus finally the purple spot, purple point, -1 times 5 is -5. Just got -5. Add all that up, multiply by 1, I get -9. So what that means is that in this region, at least some of our function is below the xy plane. So why our integral comes out negative. Place me over here. All right, on to the next one. So a double integral over some kind of region. And it looks like what we're going to want to do here is change our bounds. So some motivation for why we want to do that. If I look at this integral the way it wants me to do it currently, it's set up to do an x integral first and then a y integral. But if I look at that function, I've got e to the 3x squared times 6, which is not going to be a particularly easy integral to get done. I'd like to see some kind of a u substitution here. U, I would want to be 3x squared, meaning my du would be 6x. But I don't see that 6x show up anywhere. 6 we could deal with easily, but missing that x means that integration is going to be hard. So instead of doing x first, where I get a particularly difficult integral, I'm going to want to do y first instead, and then hope that things magically work out by the time I have to deal with x. And as we're going to see, that's exactly what's going to happen. So if we are changing the bounds of our integral, right? So if we want to, or rather changing the bounds, it's not really what we're doing. We're changing our order of integration. Changing the order of integration should not impact the integrand. So that 6e to the 3x squared, that's not going to change. Because all we're doing is just changing our order. We're not changing the function that we're integrating. We might make some substitutions in there if we were going to do some sort of parameterization in order to change our order. But we don't need to reparameterize what we've got. X and Y are going to work just fine. So our integrand doesn't change. So to highlight what's going on, I've got dx first. And x is going to float between a couple of values. Looking at the innermost integral sign, I see that my x bounds are going to be x equals 4y on the underside, and x equals 4 on the upper side. But since we're thinking about this in terms of an x integral, that should mean that we have a left and a right integration value. So where I've got some space, x equals 4 and x equals 4y. So I'm going to want to plot those two functions. So let me just grab a coordinate plane. And then I've got, we'll use my ruler to get an actual good straight edge here. One of my functions is x equals 4y. So if we think about that in terms of slopes that we're used to, that's going to be a slope of 1 over 4. So I'm going to draw it a little bit under a 45-degree angle. And I've got x equals 4. And then y, we're going to go from 0 to 1. So I'm going to also draw in a gray line at 1. That's 1 along the y scale. Down here, that'll be at 4. Label the lines that I just drew in. This guy right here is x equals 4. Over on the left, this is x equals 4y. And if I think about the way that I just set up my shape, my left bound is 4y and my right bound is 4, which means my region is the one on the lower side of that triangle. So that blue shaded region right there, that's my region. So I want to reorganize this region so that I could label my top and bottom bounds in terms of y. So I know my left and my right are 4y and 4. X equals 4y and x equals 4. But my top and bottom are going to be y equals 1/4 x and y equals 0. So if I want to change over to do my y integration first, my y bounds should be 0 to x over 4. And looking at our labels, we've got, we want to do y first. So C and D are our y values. The lower one is 0. The upper one is x over 4. And then for our x bounds, we just need our left and our rightmost values. So 0 and 4. 0 is our point for this left. 4 is our point for this right. We only need the numbers by the time we do our final integration. All right. So now that we've got all that set up, all we need to do now is evaluate that integral. So let's draw a couple integral signs. X is going from 0 to 4. Y is going from 0 to x over 4. And we still have our 6e to the 3x squared. But now we're going to do dy and then dx. So evaluating that y integral, pretty easy. There aren't any y's in our integrand. So that thing will just integrate to y, and then we evaluate it between our two bounds. All right, so this is from 0 to 4. We've got a 6e to the 3x squared times y evaluated at its upper and lower bounds. It's going to be x over 4 minus 0. And that's dx. All right, And then probably want to make ourselves a U substitution here. Let's pick another color for U. How about red? I feel like I usually use red for U. So U, in that new integration, I've got e to the 3x squared. So 3x squared is going to be my U. And that makes du 6x dx. And if I scan through the pieces that I've now got in here, I've got a 6 hanging out in front, so that's already good. I'm going to need the x from that x over 4, and the dx is already there. Dx is already there. So that means the only part that I haven't used yet is that 1 over 4 that's attached to the x. And since that's just a constant multiple, I'm going to pull it out in front of the integral so I can deal with it later. And then personally, I don't like shifting my bounds to be in terms of u. I'll just substitute back at the end so I can still evaluate from 0 to 4 for x. So I'm just going to not take that step here. I've got e to the u times du. And now all of a sudden, that is a much nicer integral than the one we were going to try to do at the beginning. E to the u just integrates to e to the u. So we're looking at 1 over 4 e to the u, which I'm just going to substitute back. That's 3x squared. And I want to evaluate this thing between 0 and 4. Which isn't too bad at all. This is 1 over 4 times e to the 48, right? 4 squared is 16. 16 times 3 is 48. Yep. And then that'll be minus e to the 0, which is just 1. So I'll end up with e to the 48 minus 1, all of that over 4. There we go. E to the 48 minus 1. And then that is the solution to our integral. I'm just going to put a star right there and label the star up there because that's where that answer should go. I'd probably type it in just like it is if it were a web work problem. Okay. In keeping with the idea of changing bounds, let's look at another one. So another one where we're going to want to change our order of integration to talk about what our shape should look like. This time we're not even told what our function f is. We're just told to set up the new bounds, but then we don't need to take the step of actually evaluating it. So let's get started with that. I'm going to need another coordinate plane. Let's go ahead and set it equal to the default black color. I don't really need the underside. So I'll just take that out. Okay, so let's take a look at our functions. This time we're doing y first and then x, and we want to switch to our new order, x first, then y. So let's see what we've got here. Our y functions, doing y first. I've got a y equals 75 on the top and a y equals 3x squared on the bottom. So let's draw in y equals 75, be up there. And 3x squared, that's going to be a parabolic shape. One more time. Good. Okay. Realsies though. This is my last shot. If I don't get it right here, I'm just gonna leave it. I lied. I want one more shot. Whatever. It's supposed to be symmetric. It's close enough. Okay. So let's label our two functions on here. I've got y equals 75 on top. Y equals 75 on top. Apparently nope, there we go. Say my pen ran out of ink. You might be wondering how that's possible for an electronic pen. Me too. There we go. Y equals 75. That's our top function. Our lower function, y equals 3x squared. All right. So those are our first functions. It looks like it defines a region pretty clearly as being that full shape that's under the line but above the parabola. But we also should be checking our x bounds because our region does not necessarily need to be the entire thing defined only by the first variable. So we look over at x. X only goes between 0 and 5. Now 5 is going to be the intersection out here. That makes sense to us. If 3x squared is equal to 75, that means x is 5. That part's good. But if x is 0, that's the y-axis right here. So x only goes between 0 and 5, as opposed to the full region, which would have been negative 5 to 5. So our region of integration is just this right half of our parabolic shape. Good enough. Cool. So that's the region we're after. Just that right half. Which means if we solve that parabolic equation for x instead of for y, we're going to end up with two solutions. One of those is going to be x equals the positive square root of y over 3, while the other is x is equal to the negative square root of y over 3. Because anytime we take the square root of a variable, we should see a plus or minus show up. So we're looking at that whole region. Its left end would be negative square root of y over 3, and the right end would be positive, x equals positive square root of y over 3. But again, we only wanted the right half, which means that our x bounds on the new integration order should go from 0 to the positive square root of y over 3. And then the y bounds are pretty easy. Y just goes from 0 up to 75. 0 because we are including our local minimum there, our absolute minimum really, down at 0, 0. And then 75 because that's our upper cutoff. And then on this one, there's no function to evaluate, so we don't even need to do it. All right, up next. So this one is out of homework set 23, which is the change of variables set. And at least for summer semester of 2023, we are not including this section in any graded work that you're going to have done. So the homework for this set is made optional. Nothing from the change of variables section will show up on a quiz or on an exam. There might be some feedback on some of the questions that'll refer to some change of variables ideas. So I want to talk about what that feedback might look like, but you do not need to use this section to solve any of the problems that include feedback from this section. We're just going to learn a new term within change of variables, and we're going to want to use that term to talk about some pieces later. So if you're going to learn anything out of section this is section 15.10 in the textbook, or homework 23, and again, it's change of variables. The one thing you should learn is the Jacobian. And Jacobian is just a term that you're going to want to know. And even without looking at change of variables, we've already been using the Jacobian. We just didn't really give it a name up until right now. So when we do integration in polar coordinates or later on in cylindrical and spherical coordinates, we need to change our integration token, which is either dA or dV, over to the new variables. And in those polar, cylindrical, and spherical sections, we just said that anytime we replace that integration token, we're going to need to multiply in some extra stuff. So in polar coordinates, that extra stuff we need to multiply in is r times dr d theta. When we look at cylindrical coordinates, it's very similar again, r times dz dr d theta. And in spherical coordinates, it's rho squared times sine phi times d rho d phi d theta. The name of that extra bit that we have to multiply in when we replace our integration token in spherical coordinates, that extra bit is the rho squared sine phi. The name of that thing is the Jacobian. And what it comes from is effectively it's a what do I want to call it? It's not exactly a cross product. It's a determinant. Yeah, it's a determinant of a derivative matrix. So up here at the top, you can see J is labeled as this 2x2 matrix that has a few partial derivatives hanging out in there. And so what happens is that if we want to change our variables, in this case, we're going to change from x and y to u and v. We'll need partial derivatives of both x and y with respect to our new variables u and v, or r and theta, if we're going to use the polar coordinate analogy. And if we take the determinant of that matrix, if we did it in polar coordinates, we'd find that by the time we're done, the determinant of that matrix is going to be r. Again, if we're looking at polar coordinates. And we'll also be looking at an absolute value of that Jacobian, because if we organize them slightly differently, we might get negative r to come out instead of positive r. So we're really just going to look at its absolute value. But so that Jacobian is the one thing you should know how to change variables. We're not going to be concerned with whether or not you can calculate one. More just if you hear the term Jacobian, you should think of the integration token that you have to spend when you switch from rectangular coordinates into polar, cylindrical, or spherical coordinates. That's the Jacobian. There's a whole bunch of stuff going on down here with how you'd actually calculate it. You can look through the example if you want. But I don't want to spend too much more time looking into it right now. Again, other than to say the important part of the Jacobian is really, okay, the Jacobian is the matrix of partial derivatives. It's the determinant of the Jacobian that we want, but quite frequently we'll use the shorthand of just calling the determinant of the Jacobian the Jacobian itself. I've said Jacobian enough at this point, but yeah, it's that little thing that we spend when we have to change our integration token to a new coordinates or new variable system. And again, that stuff is not on exam 3. So you don't need to know it. Okay, but that said, I wanted to get it all out of the way. So now we can talk about double integrals in polar coordinates. And so when we want to switch over to integrating in polar coordinates, instead of in rectangular coordinates, we need to use the replacement that dA is equal to r times dr d theta. And again, that r is the determinant of the Jacobian we just talked about. But yeah, if you just remember it's r, we're going to be good there. Speaking of which, these extra pieces are going to show up because of the way that r is really more attached to d theta rather than to dr. We usually write it r dr d theta, but it's mostly coming from the d theta term. That's where we're going to need that extra r piece in order to talk about how a point is actually changing in space. Since angles are usually thought of as have a dimension value of 0, and we'd like our dA term to have a dimension value of 2. dr's got a dimension value of 1, d theta has a dimension value of 0, but r d theta will bring it up to a dimension value of 1. You'll excuse some hand waving in there about some terms that I'm mostly making up. But I digress. Let's integrate this thing. So we want to use polar coordinates to find the volume bounded by the two paraboloids given. We'll call one Z1 and the other Z2. So how would I start there? Let's call this thing Z1. Call that thing Z2. My electronic pen is leaking ink again, because that just makes sense. And in order to calculate the volume of, calculate some volume that's in between two surfaces, I just want a difference between the top surface and the lower surface. So how about we calculate that down here? Our function of x and y, the one that we want to integrate, should be z2 minus z1. Which ought to look like 16 minus 2x squared minus 2y squared minus 2x squared plus 2y squared. Real quick on some of my thoughts here. The way that I knew that z2 specifically was the top function and z1 was the bottom function. Z2 has let's call it a z-intercept of 16, and then parabolas that open down. Something that starts high and opens down. Whereas my other function opens up because it's got positive x squared and y squared terms, but it's got a y-intercept of 0. So the other one starts low but opens up, and the second one starts high but opens down. So I'm going to want the starting high and opening down to be on top, and starting low but opening up to be on bottom. But once I get that part set up, I can simplify this a bit. This thing is 16 minus 4x squared minus 4y squared. And ultimately, it's our goal to turn this thing into polar coordinates. You might see the step we're going to take already. But in the interest of showing all of my steps, I could factor out a negative 4 from minus 4x squared minus 4y squared, leaving me with an x squared plus y squared, and then that is the thing that turns into r squared. And then I'll relabel this thing as f of r and theta now instead of f of x and y. Yeah, so that is my integrand. I will put it up here. 16 minus 4r squared. And again, this thing should be z2 minus z1. But that's not quite a complete integrand yet. That is our top function minus our bottom function. But because we're in polar coordinates, we also need to multiply by r. For the reason we talked about earlier. The determinant of that Jacobian matrix. It's our R that shows up in the dA token. Okay, so now we've got our integrand. We need to figure out what our bounds should be. So that means figuring out what our region looks like. And in order to do that, we're going to want to project our two functions, z2 and z1, down into the xy plane. Or maybe, no, we'll call it the xy plane. You can also think of it as the r theta plane, but now let's just call it the xy plane. So if I'm going to look at that projection, I'm going to need to know what this shape looks like when I have the intersection of my two paraboloids. So I'm going to set them equal to each other and see what shakes out. We got a 2x squared plus 2y squared. It's equal to 16 minus 2x squared minus 2y squared. Simplify this equation. 4x squared plus 4y squared is equal to 16. Everything's got a multiple of 4 in it. So let's simplify that to x squared plus y squared equals 4. Slide that up just a little bit. Okay, so that gives me a circle with a radius of 2. So throw some coordinate plane on there. Throw me a circle on there. It was nearly centered anyway. So there's the circle. And we want the region that's going to be inside that circle. So that's our region. We know that it's bounded by 2 and by 2 in the x and y direction, then -2 in both of the negative directions. But we don't want the x and y bounds. We want the r and theta bounds. So we want the whole circle, which means that theta be in between 0 and 2 pi. We want the whole thing. So our default option for theta is always going to be 0 to 2 pi. And we'll make some adjustments to that if we ever think we need to. But in this one, we want the whole circle, so we're going to keep 0 to 2 pi. Our radius, r, we want the entire inside of the circle, which means starting from 0 and going out to the radius, which is at 2. So that gives us our bounds. Just make sure we organize these all right. R is the first integral. So C and D for our R bounds, 0 and 2 pi for our theta bounds. All right, and now we just need to calculate a volume. We've got everything ready to go. All that's left is to evaluate our integral. So if I bring that thing over to say right here, where I've got some space. We're going to do r on the inside, so 0 to 2. We'll do theta on the outside, 0 to 2 pi. Our inside was 16 minus 4r squared times r. I'm just going to distribute that to make my integral easier to do. 16r minus 4r cubed, dr first, d theta second. And what we happen to have here is a completely separable function, meaning I can separate out my r and theta variables. It's particularly easy because I don't actually have theta that shows up anywhere, with the exception of d theta. So I'm going to split up this iterated integral into the multiple of two separable integrals. one that's a completely separated theta integral, which only includes d theta, and one that includes only our r variable, 0 to 2, 16r minus 4r cubed dr. And then I can evaluate each of those integrals. Nice thing about separating them, a theta integral is very easy. It's just 2 pi. Once around our circle, evaluate that angular rectangle. If you want to think about it that way, it's 2 pi. Over to the other side. If I integrate that thing, I'm looking at 8r squared minus r to the fourth. So that'll be 8 times 2 squared, which is 4, minus 2 to the fourth, which is 16. And then 0, and I plug in 0. So finally, simplify this thing a bit. 8 times 4 is 32. 32 minus 16 is 16. 16 times 2 pi is 32 pi. Go ahead and mark that back up here. And that's our integral evaluated. Scroll it back down there for a second. All right, and just in case you thought that double integration wasn't fun enough, we've got triple integration. Oh boy. Okay, so same idea of some of the stuff that we just did. We want to reorganize our functions and change our order of integration, just like we did in the last couple problems. But now we're going to do it with 3 variables instead of 2. I guess we didn't really never mind. I'm okay with what I said. So let's get started on this guy because it's a bit of a bear. So we want to evaluate the triple integral of some function that we aren't even going to think about as an iterated integral in 3 different ways. So 3 different orders. We're going to start with each of the 3 variables in each of the 3 iterations. So we'll do y first, then we'll do z first, and then we'll do x first. And then after that, we'll say that the other order doesn't matter a whole lot. There are technically 6 iterations that we could do to do the complete all possible orders of integration. But we're just going to look at 3 so we can primarily look at what happens first. So that's usually the most interesting or the most involved step. But again, we're not even going to care about the function we're integrating. We just want to be able to set up the bounds. So we need to define our solid region E. And we're going to say that that is in between the surfaces y equals 36 minus 4x squared minus 9z squared, which is a paraboloid, and y equals 0, which is a plane. Specifically, that's the xz plane. So y is going to be our yellow shape, or the y equals 30. The paraboloid is going to be our yellow shape. The plane is going to be our magenta shape. And I've taken the liberty of sketching that shape already because it was a little tricky to draw. But a good way to think about what the shape looks like, I know I've got a paraboloid, so I can see y equals 36 minus x squared, or I can see y equals 36 minus 9z squared. Either way, definitely have some sort of a paraboloid, and it is opening left because the x squared and the z squared terms are both negative. So it's going to have some intercept out at positive 36, and then it opens left. And hopefully I forget if this is mirrored or not. Hopefully that way is left. It's my left. It might not be your left if you're watching my camera right now. Yeah, moving on. this is our shape. We've got a paraboloid, it opens left, and then we're going to need its intersection with the XZ plane. And this paraboloid is going to have elliptical cross sections. So its intersection in that XZ plane is going to be an ellipse. And we can see that from both x squared and z squared have the same sign. So no, elliptical cross sections. So that's our 3D region. We're going to rely on that picture a few times as we try to set up what everything else is going to look like. But in order to figure out what all our bounds are going to be, we're going to want to project this shape into a few planes. In fact, the 3 basic planes. So I'm going to want to project it into the XZ plane, project it into the XY plane, and project it into the YZ plane. And I'm going to be projecting it into the plane that does not include the first variable that I am integrating. So I'm going to do y as my first integration on my first step. So first up is y. And if we look at its bounds, just thinking about the 3D shape, I need a rightmost shape or rightmost surface and a leftmost surface. So I'm doing a y integral. Y is our left and right axis. So we need a left surface and a right surface. That left surface is the plane y equals 0. I'm going to fill that in right there. And our right surface is the paraboloid. 36 minus 4x squared minus 9z squared. So because I'm doing my y integration first, I'm going to project my region into the XZ plane. I want to project it into the plane that doesn't include y anymore because I've already integrated it out. Projecting the surface into the XZ plane means I should just see that ellipse. Oh, nearly got it on my first try. That's pretty centered. So that's our ellipse projected into the XZ plane. And the region that I'm after is everything on the inside of that ellipse. Oh, don't fail me now. Fair enough. So on the inside of that ellipse, I'll need a couple of things. I'm going to need to figure out an equation for that ellipse. Fortunately, it's pretty straightforward. I projected it into the XZ plane. So y is just going to be equal to 0. So if y is equal to 0, got 0 equals 36 minus 4x squared minus 9z squared. Or alternatively, 4x squared plus 9z squared is equal to 36. That's the equation of the boundary of my region here. So if we think about our bounds real quick, we should come up with those. Our z bounds, meaning we're just going to look at the z-axis, the intersection along the z-axis. So this was our z-intercepts. Our z-intercepts, which are maximum and minimum z values, happen when x is equal to 0. So if x is 0, I've got 9z squared equals 36. So z squared is equal to 4. That's 36 over 9. Square root of 4 is plus or minus 2. So 2 and negative 2. Do the same thing for the x boundaries. These are along the x-axis, so I need the x-intercepts. That means z is 0. So 4x squared equals 36. 36 over 4 is 9. Square root of 9 is plus or minus 3. Wrong color. Negative 3 is on the left. Positive 3 is on the right. That part's not going to change. Cool. So we've got our bounds. We've got our region. Let's just go back and look at our order real quick. We already did y first, but now we want to do z second. So we're doing z second. I need to express my ellipse in terms of an equation for z. Probably goes something like this. Z squared is going to be 36 minus 4x squared over 9. And then I'll solve that thing for z itself. That'll be plus or minus the square root of 36 minus 4x squared. And that bit over 3. I can simplify the square root of 9, but I can't really simplify the square root of 36 minus 4x squared. I suppose I could pull a 4 out if I really wanted to. I guess it'd come out as a 2, but I'm going to elect to leave it as is. So if I'm doing z, I have a top bound and an upper bound and a lower bound, and those are just the positive and negative square roots because I want the entire ellipse. Probably if I were actually doing this integration, I would switch over to cylindrical coordinates to get it done because anytime I've got an elliptical or a circular shape, it's not very much fun to do it in rectangular coordinates, but I don't actually have to do the integration. I just need to set it up. So I'll stick with the bounds that they're asking for. So z is the square root of 36 minus 4x squared over 3. And this one was negative square roots, 36 minus 4x squared over 3. And last up, I need my x bounds, which means I need a leftmost number and a rightmost number. Negative 3 to positive 3. And that's our first order complete. Now let's do the other ones. So up next, it says do z first, then do y, then do x. So if I'm going to do z first, I'm going to need an upper bound and a lower bound. Let's just come back up and look at our 3D shape again. If I'm looking at a top function and a bottom function, both top and bottom from the z perspective are going to be the paraboloid. Because z is up and down. The top is just the upper half of the paraboloid. The bottom is the lower half of the paraboloid. So it's bounded on top and bottom by the same shape, which means we're probably going to be looking at a plus or minus type equation again. So that means I should take the equation of my paraboloid and solve it for the variable that I need. Doing z first, so I'm going to solve it for z. Which means I should have an equation like 9z squared. So I'll put z on a side by itself, is equal to the rest of the equation. 36 minus 4x squared, and now minus y. So moving the y over to the other side, bringing the z term over to the left. All right, so solve that thing for z. And the bounds I'm looking for are A3 and B3 respectively, just going by the labels that the question has for us. So this looks like I'm going to take the square root of both sides. One's going to be negative, one's going to be positive. A3 is the lower bound, so it gets the negative sign. Negative square root 36 minus 4x squared minus y. All that jazz over 3. And then that leaves B3 to be the positive square root. 36 minus 4x squared minus y. And it's all over 3 again. And rather than trying to write that in a tiny box, I'm just going to say that they're these two boxes right there. I'll trust that you can follow the color through the problem to figure out where those go. And they're labeled, so yeah. I'm digressing again. So we need another projection of this shape into the plane that we're going to still want to do our integration in. So I did Z first, which means now I want a top-down projection. So I want to be projecting into the XY plane. And if I do that, I should see that parabola show up. That paraboloid, rather, will show up as a parabola because we're going just down to 2 dimensions instead of 3. Ooh, that's a terrible symmetry. I'm just like curving it too much. What am I doing? Start shallower. No. All right. Well, yeah, close enough. It's a parabola. Use your imagination if you have to. Yeah, close enough to symmetric. I probably won't fit another one in. Yeah, we're gonna try. Yeah, cool. So that's our parabolic shape. It's that yellow piece, and the projection of our ellipse that's in the XZ plane is gonna show up as just a line on its projection into the XY plane. So this is our equation, y equals 0. That guy down there. And this parabolic shape is y equals 36 minus 36. 36 has a 6 in it. 36 minus 4x squared. And then let's also get our x bounds, negative 3, 2, 3, our x-intercepts. Okay, so that's the projection of our 3D shape into the XY plane. And what do we want? What do we want? We're doing Y next and X last, which works out pretty nice because we've already got our functions in terms of Y. So we can just plug those in straight up. Our upper function is 36 minus 4x squared. Our lower function is y equals 0. So 0 goes here, 36 minus 4x squared goes here. And we're doing x last again, so it's still going to go from negative 3 to 3. And that's our second one. Goes a lot faster once we get our feet wet. So in the final order, we're going to need to do x first, our last order of operations, last order of integration, excuse me, which means I need to take that paraboloid again and solve it for x. So we should be looking at 4x squared is equal to 36 minus 9z squared minus y. Reason we're doing it this way is similar to the way that we set up a top and a bottom function when we looked at our paraboloid and we did z. Our region, it just then top and bottom both ended up being the paraboloid. This time we need to do a front surface and a back surface. If we think of front being coming out of the page along the x direction and back being going into the page, sort of behind the page, behind the surface. That's our front and our back surface. And again, it is both front and back are going to be this paraboloid. So we're solving the paraboloid for x again. And we're going to get a plus or minus because we're taking the square root of a variable. So the positive surface will be up front, negative surface will be in back. So our new bounds, again, will be A3 and B3, but this time in purple. Our lower bound is going to be the negative square root. So negative square root 36 minus 9z squared minus y. All of that over 2. And the upper bound will be the positive square root. 36 minus 9z squared minus y. all over 2. And again, I'm just going to use a little purple dot to fill in those spots. Rather than trying to write that in a tiny little box. It's easier when you can type. So let's look at our new projection. So we're projecting back into the YZ plane. So we're going to see our parabola show up once again. Good enough. And that ellipse's shape projected into the YZ plane will again be just a line. This time it shows up on the Z-axis instead of on the X-axis. So y equals 0 on the right, or on the left. Y equals 0 on the left. And y equals 36 minus 9z squared on the right. Since we're projecting into the YZ plane, we'll find that x is equal to 0. So looks like we've got our shape all well and good. Let's go back and double check our new order. But this one actually says do z second and y last. It's a little unfortunate because doing y first would have been easier. But if we've got to do z next, it's not that big a deal. We just need a top and a bottom function. They are again both the parabola, which means taking that parabolic, that that quadratic equation and solving it for z. If we do, we'll get a top function, which I'll call z2. It is the square root of 36 minus y divided by 2. Or nope, not 2, 3. It was 2 when it was x. And then the bottom function, z1, negative square root 36 minus y divided by 3. So again, running out of space, I'll just mark those with a dot. And finally, we're doing y last. So y's leftmost value is 0, and its rightmost value is 36. It's that vertex of the paraboloid. They're still called vertexes in 3 space. They probably are. Cool. So there's our bounds. That's all 3 orders that it asked for. So again, we've got to change our order in some sort of triple integral situation. Usually the best first step is to, at the very least, get an idea of what your 3D shape looks like. Sketch it would probably be best, but if you're better at just visualizing, just visualize. But yeah, get some idea of what your 3D region looks like, and then we're going to need to project into some plane in order to find the second round of bounds. Yeah, that rhymed. Cool. So we got a lot of practice with setting up integrals. Let's actually do one, because that's a skill that we'll want. So enough messing around with bounds. Let's just see what happens if we actually integrate something. So we've got a triple integral in the order of dz, dy, dx with bounds given. So let's just get to it. I want 3 integrals in a row. X goes from 0 to 1, y goes from 2x to 3x. Z is going to go from 0 to 4y. Throw a splash of color in here because we're going to do z first. 3x, y, z, dz, dy, dx. All right, so whenever we're doing a triple integral, we always have to start with our innermost integral first. Unless we happen to have something that we can, if we have some sort of a separable function in a separable region, then we can separate out. And while our function looks separable here, our region is not. Since our region has variables as its boundaries instead of just numbers, we can't separate this thing out and do 3 independent integrals. We'll need to do 3 integrals in order. So let's just do that. Step 1 is do the z integral. So actually, let's just do the z integral. If I do that, I'm going to get 3 over 2 xy z squared. So mark that in magenta as well, because that's where it came from. And we're going to evaluate between 0 and 4y. Right, so that's our first step. And then we'll just add in the rest of the problem. Still 0 to 1, still 2x to 3x. We're still doing dy, then dx. Give myself more space than I needed. Let's put it right there. Cool. So that was our z integral. All we're going to have to do now is evaluate. Plugging in 0, we get 0. So let's just ignore that bit. 4y squared, 4y squared is going to be 16y squared. Multiply that in with the rest. And we're looking at 3 over 2 times 16. It's 8 times 3 is 24. Xy times y squared. It's going to give me y cubed. If I just simplify my integral that way, I'm looking at that. Throw in our integration signs now that we've got our integrand figured out. X is still between 0 and 1. Y is between 2x and 3x. I'll throw the color in because that's the integral we're doing next. Dy dx. And let's see what we get. X doesn't change, still gonna be 0 to 1. That interior, I'm looking at 24 over 4xy to the 4th, which means let's also put that guy in yellow because that's what happened next. That thing needs to be evaluated between 2x and 3x. And we'll still slap a dx there at the end. All right. One last integral to get done. We'll simplify first. Integral 0 to 1, 24 over 4 is 6. Still have an x hanging out right here. I need 3x to the 4th minus 2x to the 4th. 3 to the 4th is 81. X to the 4th minus 16 x to the 4th. Since 2 to the 4th is 16. And dx. All right. Last but not least, we actually need to evaluate our x integral. I got a little big for its britches. Let's shrink it down just a tiny bit. I'm going from 0 to 1. The function 6x to the 5th times 81 minus 16, which is 65 dx. And I could simplify 6 times 65, but I'm going to see here in a minute. When I integrate x to the 5th, I'm going to get x to the 6 over 6. So that those 6s are just going to divide away. And then I'm just evaluating 65x to the 6 between 0 and 1, which is just 65. last one ended up pretty nice. Scroll back up and make sure we fully answered the question. We have, our answer was just 65. All right, so that's an integral in triple integral in rectangular coordinates. Let's try one in cylindrical coordinates. So what do we want? The volume of the solid enclosed by a cone and a sphere. Going in between a cone and a sphere, huh? And one's cylindrical. Well, I guess is before we necessarily learned spherical coordinates, which is why it's set up this way. Normally, I'd think if I was going to do a volume in between a cone and a sphere, normally I'd think spherical coordinates would make the most sense. But I suppose cones have a certain cylindrical symmetry to them. So yeah, let's just go with what they had. Keep it in cylindrical coordinates. We're going to need to see examples with this coordinate system anyway, and I must have put this problem in here for a reason. So let's trust my old self. So if we want the volume of a shape, we want the triple integral of dv. And in cylindrical coordinates, dv is equal to r times dz dr d theta. We've already got our dz dr and d theta in there. The only thing that's missing is the r. So that's our integrand. It's just going to be r. Up next, volume that's enclosed by a cone and a sphere. So if I'm thinking about this shape, it's going to look a lot like an ice cream cone, an upright ice cream cone. Our ice cream is going to be made up of the sphere. The cone is going to be made up of the cone. And it's, in particular, it's a waffle cone, one that comes to a triangular base, not one of the like cheap plasticky kind of cylindrical cones. No, this one's comes to a nice point. Think, classic waffle cone with a scoop of ice cream on top. So that means that our top function is going to be the ice cream, which is the sphere. Our top function is going to be the sphere. This guy right here is going to be Z2, so that's our sphere. Our lower function is going to be the cone. So this guy is Z1. And seems like we probably want to express those functions in terms of our cylindrical coordinates. So let's do that. Z1, which initially was the square root of x squared plus y squared, that has a very nice translation into cylindrical coordinates. Square root of x squared plus y squared is r. That's awful nice. For the sphere, Z2, I'm actually not going to set it equal to Z2. I'm just going to label it as Z2 because Z isn't going to, we're not going to solve it for Z itself. X squared plus y squared plus Z squared equals 8. X squared plus y squared need to go, but that's nice because it's just r squared. Z squared can stay because we are in cylindrical coordinates, so Z is valid, still equal to 8. So those are our two surfaces, an upper surface and a lower surface. So what's up next? We probably want to find the intersection of those two surfaces. So if we think about, because we're going to do Z first. Okay. not get ahead of ourselves. We're doing z first, so let's go ahead and plug our bounds in. We're doing z first. Our lower bound is the cone, and our upper bound is the ice cream. Because our ice cream is oriented so that it doesn't fall out of the cone, it's up on top, we're going to want the positive square root when we solve for z. So solve for z, move the r squared over to the other side, take the square root. We're looking at the square root of 8 minus r squared. 8 minus r squared. And again, we're taking the positive square root here because we want our ice cream to not fall out of the cone. Cool. So we've got now our z bounds figured out. We got to do r and theta next, which means we're going to want the projection of our ice cream cone down into the xy plane. So that projection, if I'm looking, projecting it straight down, that projection is just going to look like the intersection of the cone and the ice cream, the intersection of the cone and the sphere, which means I need to set these two equations equal to each other rather than just setting z equal to 0, because I want the intersection of the surfaces, not just z equals 0. So set our surfaces equal, z1 equals z2, and that's going to mean that I have r squared plus r squared is equal to 8. So when I'm saying we're going to set them equal, really it just ends up being a substitution is the easiest way to set them equal to each other. I already know that at their intersection, z should be equal to r, so I'll just replace z with r, meaning 2r squared is equal to 8, or r squared is equal to 4. So if we think about, cylindrical coordinates and what that means, we're just looking at a circle with a radius of 2, and we want the whole ice cream scoop, which means we're going all the way around the circle. So r is in between 0 and 2, and theta is in between 0 and 2 pi. So again, we're always going to think of 0 to 2 pi as our default option for theta. And unless we have some reason that we should be restricting some elements out of here, we'll just use 0 to 2 pi. So it's always our first thought, 0 to 2 pi. And then we'll go through and if there's only a particular slice of the circle that we want, we'll start restricting theta from there. But as long as we want the whole circle, if we want to go all the way around all 4 quadrants, 0 to 2 pi is our answer. So we have our new bounds. So let's fill out the chart. 0 to 2 pi, 0 to 2. And we ought to be ready to calculate this volume. So let's set up a triple integral. 1, 2, 3 integrals. We're going to do z first, which is r to the square root of 8 minus r squared. We said we'd do r next, so 0 to 2, and theta last, 0 to 2 pi of r times dz dr d theta. So there's our plan. So let's do our integration. Z is up first. So we'll leave our r and theta elements alone. That thing is going to integrate to r times z, evaluated between our two bounds. This will look like r times the square root of 8 minus r squared. minus r times r. Still dr d theta. R is going to go from 0 to 2. And theta is going to go from 0 to 2 pi. And now something nice has happened for us. Initially, we did not have a separable series of integrals because we have variables in our bounds. But after we resolved the z integral, everything else just has constants in it. Our function itself is separable. We'll have that whole thing times dr times 1 d theta. So we can do the r and theta integrals separately or independently, and then just multiply them together. So conveniently, our theta integral is just 2 pi. Nice and simple. 0 to 2 pi, integral of d theta. We get a solution of theta, 2 theta. Blah, blah, blah. Looks like we should do that other integral as well, though. So, let's see what happens. Okay. That first nest, we're going to need to do some sort of a u substitution, probably call it 8 minus r squared. That makes du negative r over 2. So this first guy should integrate to negative 1/2 times 8 minus r squared to the 3/2 power. That'll be the integral of the square root function. I'm missing an element though. I need to divide by the new power, so multiply by 2/3. There we are. Minus, well, integrate r squared. That one's a kindness. That'll integrate to r cubed over 3. Easy peasy. This thing should be evaluated between 0 and 2. So now all we've got to do is plug some stuff in. So we're looking at still 2 pi. That element won't change just yet. Times, we plug in some other stuff. Well, negative 1/2 times 2/3 is just negative 1/3. So I'll simplify that. 8 minus 2 squared. It'll be 8 minus 4, which is 4. To the 3/2 power. Resolve that in a minute. Minus, we're looking at 2 cubed over 3. 2 cubed is 8. Minus the second half of the integration. Minus. This will be negative 1/3 times 8 minus 0, which will be 8. To the 3/2 minus 0. 0 cubed over 3 is just 0. Close that order of parentheses, close the first order parentheses. There we go. A complete line. All that's left from here is to simplify. So I'm going to have a 2 pi still floating out in front. I've got a factor of 1/3 on every term, so I'm going to factor that out as well. Call it a 2 pi over 3 and simplify the bits that are inside. The only term that's going to come out positive is that 8 to the 3/2 over in the second half. I'm going to list that one first, just because I like to list positive terms first if I can. So 8 to the 3/2. minus the rest of it. So after I've pulled the 3 out, 4 to the 3 halves, square root of 4 is 2, 2 cubed is 8. So I've got a negative 8 minus 8 resolves to a minus 16. And then that other term is 0. So there's our volume. Space that out just a little bit more. Cool. And there we have it. That's an integration in cylindrical coordinates. Oh, what fun. Apparently I slipped into a Christmas jingle for a moment. Sorry about that. Um, let's bring it back. So we've got another cylindrical integration that we'd like to do. And what's going on with this one? So if we were to sort of evaluate the differences between the two problems we're looking at, let's see. In the first one, right. So the first one, we were told a couple of surfaces, a couple of quadratic surfaces, and asked to calculate the volume of that shape. This one now isn't asking us specifically for a volume. It's just giving us a triple integral that is right now set up in rectangular coordinates. And if we're looking through it, rectangular coordinates look like a bad choice because we've got a whole bunch of x squareds and y squareds coming in together. It just looks like cylindrical or spherical coordinates is going to be a much better choice. This one's kind enough to tell us we should use cylindrical coordinates, although I believe on the exam you'll get your choice of whichever system you want to use, which can be both it's a blessing and a curse. So one hint that I'll want to say about the integration that you'll do on the exam, when you're doing triple integrals, you've got your choice of 3 coordinate systems: rectangular, cylindrical, and spherical. Because we're not doing change of variables, which means you won't need to consider other systems. But within those 3 systems, if we're asking you to do an integration on the exam, one of the coordinate systems, or maybe one of the orders for integration, is going to be algebraically easy, whereas most of the other systems are going to be quite difficult. So if you're working on an integration on the exam and you're doing a bunch of hard math or a bunch of hard arithmetic, hard algebra, stop and rethink your strategy. None of the arithmetic or algebra on the integration questions should be difficult if you get it in the right order. So the questions on the exam are going to be much more about identifying the correct order or identifying the correct coordinate system and then doing the integration that way. Yeah, if you're trying to bust out like some inverse trig integration, you are definitely going down the wrong path. I know there was at least one WebWork question that asked for some sort of arctangent integration, but we don't do that here. So don't go down that path. Change to a different system. But enough about that. Let's talk about the problem in front of us. So we're going to want to take this thing and switch it over to cylindrical coordinates. So we want to switch from dz dy dx to dz dr d theta. So let's knock out the easy one first. Z happens as our first integration in both orders. So z's bounds basically aren't going to change. It's still going to go from z equals 0 to z equals 25 minus x squared minus y squared, but we're changing our variables now. So instead of 25 minus x squared minus y squared, just 25 minus r squared. So we'll just make that simplification, that change over to r. The rest of it, we're going to need to know what our region looks like in order to figure out what our bounds are going to change to. As Alex said, Z's bounds didn't really change, but X and Y are switching over to R and theta. So let's take a look at what we got. Give me some coordinate axes. It's probably bigger than I need. Yeah, this will do nicely. So I've got the equations over on the right for the y integrals. I've got y equals the square root of 25 minus x squared and y equals 0. That top equation looks an awful lot like a circle. So just wasn't a very good circle. Let me try again. That looks a little bit better. So I've got a circle, y equals 25 minus x squared, but I've also got the line y equals 0. So y equals 0 is this guy. Y equals square root 25 minus x squared. I said it looked an awful lot like a circle, but it really looks like is an awful lot like the top half of a circle. Meaning I don't really need the bottom half over here. So just from the y bounds, I know that my shape's going to look kind of like this. I should also go check the x bounds. They're -5 to 5. This is a circle with a radius of 5. Those are our x bounds. Our shape must be this half circle. So that's our region of integration. If we go talk about our variables, we know that R, we want to start from the origin and go all the way out to the edge of the circle. So R, nice and easy. It's 0 to 5. Theta is the other one we want to do. Remember that our default choice for theta is always 0 to 2 pi. So I'm going to start by thinking 0 to 2 pi. However, on this problem, I found that I only wanted part of the circle. Right? In fact, I only want the top half of this circle. So looking at the bits of the circle that I want, I'm only after the first two quadrants, quadrant 1 and quadrant 2, which means instead of going from 0 out to 2 pi, I still want to start at 0 because theta equals 0 is this guy here on the right. That's our positive x-axis. But if we follow theta through its rounds, here, 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 I'm stopping at theta equals pi. So my bounds on this one are going to be 0 to pi instead of 0 to 2 pi. Because again, I only want the first two quadrants. So from 0 out to pi. So my theta bounds, 0 to pi instead of 0 to 2 pi. My R bounds, 0 out to 5. And we also need to switch over our integrand. We had 8 times the square root of x squared plus y squared. But really, that's just 8r. We switch that over. And don't forget, if we're going to be integrating in cylindrical coordinates, we need to change our integration token to include that multiple of r that shows up. Again, from the determinant of the Jacobian, now that we know that thing's got a name. Cool, and now that we have that, We just need to calculate the integral. Get everything set up. All that's left is to just do it. So 1, 2, 3 integral signs. Our integrand is 8r squared. And we're going in order of dz, dz, dr, d theta, where z goes from 0 to 25 minus r squared. Saying about the last problem for a second. R going to go from 0 to 5, and theta from 0 to pi. All right, and looks like we're ready to do this. So give me 2 more integral signs. We're going to do z first. So 1, 2. What do we get if we integrate that thing? It'll be 8r squared times z. Z goes from 0 to 25 minus r squared. So I've got 8r squared times 25 minus 8r squared times r squared. That ought to simplify to, I don't like the look of these integral signs. So that simplifies to 8 times 25, which is 200 r squared minus 8r squared times r squared will get me r to the fourth. dr d theta. For clarity's sake, I'm going to scooch this down just a little bit. R, we know, goes from 0 to 5. And theta goes from 0 to pi. Now my function is separable again. My bounds are just whole constant numbers. They don't need to be whole numbers. They just need to be constants. So my bounds are constants, meaning I have a separable integral again. So I can do these independently. This time the theta integral just goes to pi rather than 2 pi. The r integral is a bit more exciting. I only need to evaluate it at 5, so let's just take that step all at once. I'm gonna get r cubed over 3. So this will be 200 over 3 times 5 cubed, which is 125. That one I do know off the top of my head. Minus 8 over 5 times r to the 5th. 5 to the 5th power, though. I don't actually know that one. I know 5 to the 4th is 625. That's just 25 squared. I don't happen to remember 5 to the 5th. Fortunately, I don't really need to remember it to even do the mental math on this problem, because I can just divide one of them away with the 8 over 5. So simplify what we got going on in there. 200 times 125 is going to get me to 250, a couple extra zeros tacked on, so 25,000. Divide that thing by 3 minus 8 times, well, I've got 8 times 5 to the 4th. So 8 times 25 squared. That can't be too hard, right? 8 times, what's the smartest way to do this? Oh, I've got 2 cubed times 5 to the 4th. That's smart. Yeah, so that'll be 10 cubed times 5. That gets me to 5,000. Some Common Core mathematics or something, if ever I've seen it. Okay. Now that seems about as good as it's gonna get. I can factor some pieces out of here. Looks like 5,000 will come out of both. Let's call that 5,000 pi. times the leftover bits. 5/3 minus 1. So that inside will simplify to 2/3. 2/3 times 5,000 is going to be 10,000 over 3. So 10,000 pi over 3 is our solution. Pretty sure you've got access to calculators. So you did not need to do all the mental math I just did. I just plug that into a calculator and get an answer. But, you know, some might say that's a skill worth having. Probably both parts. All right. I've rambled enough. Let's take a look at this next problem. Okay. We want to express the volume of the sphere, which is a sphere with a radius of 5 centered at the origin that lies in between two cones. So in between, two cones that are listed there. Let's call it which way are you gonna go? Well, we'll call them a yeah, this is still gonna be fine. Give me a Z1 and a Z2. I haven't thought too hard about which one goes where yet. So, with that said, I want to solve for this stuff first. Or do I want to draw a picture first? I think I feel like doing the algebra first. So, let's do it. Oh, I get to solve for 2 of them. So, yeah. Since I get to solve for 2, I'm going to go through 2 different methods. One of which I tend to prefer more than the other, but I feel like every time I try doing it my preferred way, most of you guys as students generalizing there. But a lot of students tend to not like my favorite method. It's too bad because I like it kind of a lot. But I'm rambling again. Okay, let's solve Z1. Z1. That is giving us the equation z equals the square root of 3x squared plus 3y squared. And I'm going to take a quick step over here, pull the square root of 3 out. Getting me to this function. Z is equal to the square root of 3 times the square root of x squared plus y squared. And let's start working to simplify this thing. So here's a leap that you kind of got to get through. Seeing the pieces that I have here, a square root of x squared plus y squared and a z hanging out on opposite sides of the equal sign, I'm thinking about the identity tangent of phi is equal to the square root of x squared plus y squared over z. So that is one of the substitutions that we can use to switch between spherical coordinates and switch between spherical coordinates and rectangular coordinates. It's not one that's no, this identity is still true. We run into a bit of an issue though, because the arctangent function is ill-equipped to deal with uh, the tangent function is ill-equipped to deal with all values that we want to use for phi. I think I said tangent function, but what I meant was the tangent inverse function is ill-equipped to deal with all of the values of phi that we'd like. Tangent inverse as a function needs a particularly wonky domain because we don't want to cross the asymptotes that the tangent inverse function has. If we well, back that up. The tangent function has a lot of asymptotes. And when we define our tangent inverse function, we don't want to cross any of those asymptotes, meaning that its domain ends up being defined between negative pi over 2 and positive pi over 2. I think I misspoke again. The tangent inverse's range is defined between negative pi over 2 and positive pi over 2, meaning that we're pulling the domain negative pi over 2 to pi over 2 from the tangent regular function. But ended up on a bit of a tangent there again. Surprise, surprise. That's the identity that I kind of want to go for here. So I want to set up a square root of x squared plus y squared over z. And it looks like I'll just do that on the right side. Square root x squared plus y squared over z, meaning that the other side of the equal sign needs to be 1 over root 3. All right, from here, let's simplify some pieces. Yeah, put it over there. On the right side, this is tangent phi. I'll use blue for phi and green for theta, just so we don't get any of our angles mixed up. So using some color tends to help keep them separate. So tangent phi on the right. On the left, I've got 1 over square root 3. I can rationalize that to square root 3 over 3. Hopefully you recognize one of those two options on the left as a tangent value that you know off the unit circle. Just kind of depends on your trigonometry course, or if you took trigonometry or pre-calculus. I've seen those get defined either way. But I usually remember the rationalized version, square root of 3 over 3. It's got 2 3s in it. So that must be a tangent value at pi over 6, because 6 also has 2 3s in it. Helpful little trick. So phi's got to be pi over 6 on that cone. So that gets us directly from rectangular coordinates to spherical coordinates. Bleh. Can already tell I've been talking too much. Okay, so I'm actually going to scoot that down a little. Yeah. Let's solve the other cone, Z2. So what we just found out, in spherical coordinates, cones can be rather easily expressed as simply phi equals an angle. Phi equals a constant number is going to describe a cone in spherical coordinates. Blah, 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 blah. Spherical coordinates. Nope. Let's move past that. Let's solve Z2, but now I'll do it the way that I kind of prefer. So oftentimes when I'm solving or translating from rectangular coordinates into spherical oftentimes when I am translating from rectangular coordinates to spherical coordinates, I find it's easy to stop off in cylindrical coordinates first. Ugh, man, okay. So I'm going to do a quick change from rectangular to cylindrical, and then complete the change into spherical. So just like last time, I'm going to pull out a 1 over root 3 and leave behind an x squared plus a y squared. And then call this thing z equals 1 over square root 3 times r. Because I think that can be helpful. And then that way I can, get rid of I don't have to deal with that square root of x squared plus y squared. Then I can use some substitutions that I know for z and for r. Like for example, z is equal to rho cosine phi. Too much color, it's not relevant. Z equals rho cosine phi. And r is equal to rho sine phi. Those are a couple of helpful substitutions here. That way I don't need to specifically get the square root of x squared plus y squared over z. Now I can just start trying to solve this thing for phi, which means multiplying a square root of 3 over to the left side, dividing rho away from both sides. Rho ends up not being relevant to this equation. On the right, I'm going to get sine over cosine, which is tangent of phi. And then once again, get a value off of the unit circle. This thing is pi over 6. Nope, pi over 3. Pi over 6 is the last one. The tangent of pi over 3 is equal to square root 3. Again, be careful with the tangent inverse function because it doesn't always give you the answer that you want. Tangent inverse works just fine in the first quadrant, but if we need any values in the second quadrant, tangent inverse is going to fail us. It's going to give us values in the negative fourth quadrant instead. So again, all of the inverse trig functions get wonky definitions, so just be careful if you use them. It's usually better to just set up a regular trig function like tangent pi equals root 3, and then use the unit circle to figure out your value from there. But cool, I've got my equations in my two cones. It's pi over 6 and pi over 3. Now that I've gone through all of that, now let's go sketch the region. And if I'm doing it the way I thought I did, yep, I already pre-drew this picture. So here are our two cones. Phi is equal to pi over 6 and phi is equal to pi over 3. So remember that phi is measured from the positive z-axis. So smaller angles are going to be closer and tighter to the z-axis, whereas larger angles are going to be wider, further, and I guess looser from the z-axis. So the large angled cone opens up wide, the small angled cone opens up tight. And if we're thinking about our progression of phi values, we know it's measured from straight up and then measured out from there. This means that our lower phi bound is going to be pi over 6, and our outer phi bound is going to be pi over 3. So pi over 6 should go on the bottom, pi over 3 on the top. We'll know we got them backwards if at the end we get a negative value for our volume. So it's not the end of the world if you end up swapping these bounds. You'll just get the negative volume instead of the positive volume. If that happens, you just, take the positive value instead of the negative one. Yeah. So I suppose one of the things I should mention here, if you're asked to find a volume on the exam, volume is always going to come out positive. If you get a negative answer for the volume, rethink what you did. Sometimes it's as easy, you just got some bounds backwards, so you just take the value as is. Other times it might mean that there's a more serious calculation error that you'll want to look through your work and find. But yeah, so these are our cones. One's on the outside, one's on the inside. So let's come over here and I suppose I'll label that one in blue. So that's our outer cone. versus our inner cone. Cool. But so that means that we are looking at the space. What color do I usually use for the other stuff? We are looking for the space. This thing is going to be a sphere. Might be something. This is not a very good drawing of a sphere. Yeah, whatever. We're looking at the sphere that is the bit of the sphere that's in between these two cones. So kind of like this area in there. I just don't really like the way that those came in, so I'm just going to erase them. But yeah, so we want the area that's in between those two spheres. We're going all the way around the circle in the XY plane. So we're going to get to keep our usual values for theta. Theta gets to be between 0 and 2 pi. Our 3D radius rho goes from the origin, which is at 0, all the way out to the edge of the sphere, which we saw earlier. Our sphere had a radius of 5. So rho is between 0 and 5. And then we just have to integrate dv. So let's do that. So a couple of other things that maybe I should write down, some identities that I wanted to use here. Tangent of phi, I think, is always easier to remember as the identity r over z rather than square root x squared plus y squared over z. This one just makes more sense to me, because if I want to think about what phi looks like in 3 space, it's easiest to think of it as a triangle where one edge is the z-axis, and back that up. So if I want to think about phi, one element of phi, the hypotenuse of the triangle that contains phi, is going to be the 3D radius rho from the origin out to the point. The adjacent side to phi in this triangle is going to be the z-axis. And then the opposite side in that triangle needs to connect our point out in space to the z-axis. So I'm going from the point straight to the z-axis instead of from the point back to the origin. That distance is r, the radius that we use in cylindrical coordinates, not the radius that we use in spherical coordinates. Bleh. But thinking about my triangle that way, the opposite side is r, the adjacent side is z, and then the hypotenuse is rho. That's what I think is the easiest way to remember phi. Because that way, phi doesn't really depend on our angle theta at all, which means that I think it's easy to remember r over z than it is to remember the slightly more complicated formula that tangent of phi is equal to square root x squared plus y squared over z. So again, that's why I tend to prefer the second method that I used when I was solving for phi rather than the first. But you can see either one is going to get you to an answer. So you get to use whichever one you like the best. I'm not going to be picky. But okay. From here, we're basically ready to go. We just need to set up our integral. We've got almost everything there. Let's just rewrite our bounds. Theta was between 0 and 2 pi. Rho was between 0 and 5. And let's do a triple integral. So 1, 2, 3 integrals, because we're getting a volume. Oh, crap. Pen has run out of ink again. Probably actually means my tablet's overheating. It likes to do that. All right, so try me one more time. There we go. It's back. So I need a triple integral of d rho goes from 0 to 5. Then I've got a d phi. But that's going to look like rho d phi, where phi goes from pi over 6 to pi over 3. And then I need an r d theta, where r is rho sine phi d theta. And that goes from 0 to 2 pi. And if we look at our bounds, all three pieces are constant numbers. If we look at our function, it's also completely separable. I only have a single term. So I just separate out each piece into the multiplication that I want to be doing. So I can separate this triple integral into 3 independent single integrals. So let's do that. First up, I'll do the theta integral, 0 to 2 pi of, this is just d theta. It's the only theta that shows up in our function. Times, up next we've got our phi integral. I do have an element for phi though. I've got a sine phi. So sine phi d phi goes from pi over 6 up to pi over 3. And lastly, a rho integral. And I've got 2 rhos getting multiplied together. So rho squared d rho goes from 0 to 5. Looks like I'll need to make myself a bit more space. I'll do that real quick. All right. And then I can just resolve each of these 3 independently. Integral of d theta from 0 to 2 pi is 2 pi. Nice and easy. Sine phi, that'll integrate to negative cosine phi. And I need to evaluate negative cosine phi at those 2 angles. Cosine of phi of pi over 3 is 1/2. So that'll be a negative 1/2 minus another negative cosine. So it'll end up being plus cosine of pi over 6. Cosine of pi over 6 is root 3 over 2. And lastly, our rho integral, rho cubed over 3. That'll be 5 cubed over 3. So I'm just evaluating from 0 to 5. So I can put this all together. I'm looking at 5 cubed times pi. That's 5 cubed over 3, so let's keep it at over 3. I'm going to multiply the green 2 into the blue set of parentheses to reduce that denominator. I'm left with root 3 minus 1. And I suppose I'll leave this as an exact answer in the notes. And next, are we to the almost to the end? So yeah, I think after that, I'm just gonna talk about some completed problems. So last one, what do we got? Identifying surfaces based on their spherical or cylindrical equations. What are these things going to look like? So Starting with that first one, phi equals pi over 2. We saw in the previous problem, anytime we have phi equals a constant number, we're going to see a cone. There's one exception to that rule, and that's this equation. Because if phi is equal to pi over 2, that's the same thing as z is equal to 0. So if we come back up to that the diagram that we had earlier, where we have these cones, the cone is, just described by the equation phi equals an angle. If we keep, loosening up these cones, we can think of them like flattening out the cones. The larger the angle gets, the more flat the cone becomes because it's getting further away from the z-axis. If we flatten out that cone enough, it's just going to become the xy plane. If we laid it all the way flat, that corresponds to an angle of pi over 2 for phi. So most of the time, if we see phi equals a constant number, it's a cone, unless that constant number is pi over 2. So surface, phi equals pi over 2 is a special case, and it is a plane rather than a cone. Specifically, this is the xy plane. So one special case that you'll want to be aware of. Phi equals pi over 2 is the xy plane. Then next up, if we just have rho equals 2, rho equals a constant number, that's about the easiest equation we can have in spherical coordinates. Oh, man. That's the equation of a sphere. It's equal to a constant number. Then the next one is kind of expecting you to remember some things about polar coordinates and some graphical units that we would have done back in Calc 2, or perhaps even longer ago. We might have seen this in an algebra class when we studied polar coordinates there. Usually that's only if you see like an advanced algebra 2 course really gets into polar coordinates. But so the question's kind of expecting you to remember some stuff about what those polar coordinate equations would have looked like. And if you remember that stuff, great. This one's going to be easier than you might have thought. But if you don't remember that kind of stuff, maybe we should look at some other values here. So what we might want to do is sketch out some points for this plane, or for this surface. And so what I want to do is think about, what do I want to think about here? Let's think about the YZ plane. A couple of reasons why I want to think about the YZ plane. I see that I've got a sine theta and a sine phi. Anytime I see phi get involved, I know I'm going to want to be considering the z axis, because phi always describes z. I've also got a sine theta that shows up. Sine theta usually means I want to be thinking about y instead of x. And in particular, I could have the equation rho sine theta sine phi is y. So what I'd probably do here is if I could sketch out this shape real quick. I'm gonna want just a 2D set here. That ought to be good enough. I don't care to look at the negative y direction. So let's just take that out. So I'll put z up there. I'll put y down here. The nice thing about looking at the zy plane, that means that theta is equal to pi over 2. So sine theta is just going to be equal to 1. So if I run through some angles for phi real quick, If phi is equal to 0, I'm going to get the point that is at the origin. It'll be right there. Another easy one, if I think about phi equal to pi over 2, that means I'm going to be along the y-axis. Phi equals pi over 2 is the xy plane. And if I'm already looking at the zy plane, it means phi equals pi over 2 is just the y-axis. If I bring phi back around to pi, I get sine of pi, which is, wait a second. Yeah, sine of pi, which is 0, once again. So phi equals pi, it brings us back to this purple point. So I'm going to have something that's going on in like the positive YZ plane. Let's also sketch some other lines in here. Let's go with phi equals pi over 4. And phi equals 3 pi over 4. So that'll be 45-degree angles measured from the z-axis. Throw some other labels on here. This is phi equals pi over 4. This one's phi equals 3 pi over 4. And if we look at the radius that we've got here, sine of pi over 2 is 1, which means my radius is going to come out here to 5. But if phi is anything that's not pi over 2, sine is going to be less than 1. So I'm going to have 5 times something less than 1, meaning the points along these lines shouldn't go out quite as far as 5. So maybe it's like here and here. These things should be symmetrical. And you can kind of start to think about, if I run through other angles for phi, I'm going to have to start by going up, but with really, really small. And then the more I go out, the larger rho can become, but then it's going to have to shrink as it comes here. And I have this shape on screen, which looks a lot like a circle. The only reason it looks a lot like a circle instead of exactly like a circle is because I drew it instead of a nicer shape. So we're going to see a circle show up. If we try to sketch this region out, we could do something rather similar for the XZ plane, or rather than the XZ plane, we probably want to look at the XY plane. So let phi be equal to 1. We'll see another circle show up there. This shape is describing another sphere. So going through a quick sketch of the region, this is what I might see. That's one way of trying to solve that equation out. Is thinking about it graphically. And I did it this way first, because we'll look at a second option in the second question, where we could look at it algebraically instead. Very similar equation. Rho equals 8 cosine phi instead of rho equals 5 sine theta sine phi. These two equations should be reminding you of rho looks something like z for the second one, or rho looks something like y for the top one, for that first one. And that is going to be the guiding principle we're going to use to solve this thing out algebraically. So if I see a cosine phi sitting by itself, rho equals 8 cosine phi. Seeing a cosine phi by itself, that makes me think that I should probably be multiplying the whole equation by rho. So there are a couple of things I think about when I'm trying to transition from spherical or cylindrical or polar coordinates back to rectangular coordinates. And those are, if I see a trig function sitting by itself, I should probably multiply the entire equation by the radius. Or if I see a radius sitting all by itself, I usually like to square both sides, but I do it in that order, right? So my first order thought is trig equation by itself, multiply both sides by rho. If I see rho sitting by itself, square both sides. But that's my secondary thought. I've got a trig function sitting by itself, so I want to resolve that first. Then if I had a rho sitting by itself, I'd square both sides. So as it turns out, multiplying both sides by rho accomplishes both goals in this problem, which is why I think multiply by rho first if I've got a trig function by itself. So if I do that, what am I going to get? We'll get a rho squared over on the left. And on the right, 8 rho cosine phi. Reason I did that is because then I get a particularly nice element that shows up in this rho cosine phi. That is an exact substitution for z, which is particularly nice. 8z over on the right. And on the left, I've got rho squared, which is also a very nice substitution. X squared plus y squared plus z squared is rho squared. So one of the reasons why I don't like to be substituting why I don't like a rho all by itself is if rho is by itself, I'm going to have a plus or minus that shows up, and I'd rather not deal with plus or minuses if it can be helped. So I'd rather have a rho squared first. So already you're probably seeing something that looks an awful lot like a sphere show up, because I've got that x squared plus y squared plus z squared. A whole lot like a sphere equation. The other side is 8z, which isn't great just yet, so I probably want to simplify it a bit more, but I should be able to get this to something that's recognizable. So I am going to move that 8z over to the other side. Say it's equal to 0. I'm also going to leave myself a bunch of space for a reason that I'm going to talk about. Right meow. So I've got a square z term and a linear z term going on. And I want to put this into the form of an equation that I recognize, which means I'm going to complete this square, which something that doesn't happen all the time once you get beyond an algebra class. But we're going to do it here regardless. So if I want to complete the square on this thing, z squared minus 8z, that complete square should have a plus 16 here. Since in a complete square, that middle term should be 2 times whatever the squared number is. So half of 8 is 4, meaning I wanted to simplify this thing down to z minus 4 squared. That was my goal. That's what I wanted to do. But in order to add 16 to the left side, I also need to add 16 to the right side, because I've got to keep this equation balanced. And then I can simplify it's not even any more simplification to be doing. I just have to write the rest of the equation back in. X squared plus y squared plus z minus 4 squared is equal to 16, or 4 squared. So what I ended up finding is that this equation is a sphere. It's got a radius of 4, and it's got a center that has been shifted 4 units up the z-axis. So it's got a center at 0, 0, 4 instead of 0, 0, 0, instead of the origin. So once again, I found that this thing was a sphere. And I could do a very similar algebraic trick to the equation above, where I'd see a rho squared equals 5y. Just again, multiply both sides by rho, and then quite similar simplification. I'd complete the square for y instead of completing the square for z, but I'll see that it's another sphere, but it's been had its center shifted along the y-axis instead of along the z-axis. All right, so I think that's the end of the calculation type problems I wanted to look at. So I picked out a few other things that I want to review from the notes, or maybe some other completed web work assignments or web work problems. Where I'm not as interested in doing the whole problem, but rather I want to talk about a specific element that shows up. First of which on here, volume of a sphere, 4/3 pi r cubed. It's an equation you should know because there will be times when you might need volume of a sphere for something. I don't think that's a formula that's given on the problem where you need it, but since the exams are open note, you should have access to that formula. So no volume of a sphere. It's 4/3 pi r cubed. I don't think you'll need surface area of a did I say volume of a cube? Because that's volume of a sphere. No, been talking too long. I don't think you'll need surface area of a sphere, not yet anyway. We're definitely going to use it in the post-exam 3 content. Don't think you need it now, but in case you did, surface area of a sphere is 4 pi r squared. Looks a lot like the derivative of the volume of a sphere. Volume of a cylinder also might show up. It's pi r squared times z, pi r squared times h. Think of it either way. Just the area of a circle times the height of the cylinder, or the area of your base times the height of the cylinder, because we could have non-circular bases. But whatever. I wrote down volume of a sphere. That must be the one that I think you need. So volume of a sphere, it's right there. Other things. So I believe this is, Fubini's theorem is the one that I've used a few times. This is the one that says if I have a separable equation and my bounds are constant numbers, I can separate out an iterated integral into two separate, two independent single integrals. And Fubini's theorem also has an application into 3 space, which works much the same way. If I have a triple iterated integral, I can break those apart as well, as long as I follow the same rules. Separable function and constant bounds. So this is Fubini's theorem. We talked about it in section 15.2. And then a quick explanation of what is and is not a separable function. I can say my function is separable if I can factor out all of my variables. So something like x times y is a separable function because I need to be separating based on multiplication. Something that is not separable would be x plus y, because I cannot factor one variable completely out. So I need to be separable based on multiplication, not separable based on addition. X plus y is not separable, but x times y is separable. So notice the green check versus that red x. So here's the formal statement of Fubini's theorem, which says that as long as my bounds are whole numbers, I can simply switch the order of integration. That's what Fubini's theorem is doing here. So I guess that's the real Fubini's theorem, is just saying I can switch my order freely under a very specific integral type. It's just that if we take an extra step and also have a separable function, we can apply Fubini's theorem to completely separate our integrals. So this is Fubini's theorem. Notice the highlighters that are going on here. The green versus the purple integral tokens and bounds. If I'm integrating over a rectangular region, meaning that all of my bounds are constant numbers, I can simply and freely switch the order of integration. And again, that's as long as all my bounds are constants. As soon as I get variables in my bounds, that's when I've got to, like sketch my region and be particularly careful if I'm switching my order. But if the bounds are constant, I can switch them freely. So, if you're watching this before you take the exam, there's probably a true false question that might get tricky with these bounds. So pay careful attention to the bits that are highlighted on the true false section. You might see one that comes up that involves Fubini's theorem. Then up next, I think I may have even put the question on the review. The average value theorem. If I need the average value over some 2D region, it is the integral of my function divided by the area of that region. So that function could be any number of things. I know that there's an example that we looked at that was the distance from the origin, in which case my function is simply r. R is the distance in a 2D space anyway. R, the radius, that's the distance from the origin to any point. So I'd want the double integral of r dA divided by the area of the region, which could also be expressed as a double integral, just the double integral of dA itself. That can also expand up to average value over a solid, so a 3-space 3D shape, in which case it's the triple integral of the function divided by the volume of the solid. So I thought I'd highlight that formula because I must have thought it was important. So know the average value formula. What else? Oh, right. This guy. I think this was just a trickier question on one of the quizzes. This must have been on quiz 8, the one that we just took. So looking at the orders that we've got here, I think the z bounds are pretty straightforward. It goes from z equals 0 up to z equals y. So that'll just be a diagonal plane expressed here as a line. The other z equals 0 plane, that's the xy plane. I think it's the y bounds that end up being tricky on this one. We're going between y equals 0 and y equals x squared, which is the yellow shaded region that's on screen in front of us. Yeah, because then x goes from 0 to 1. So you wanted to be careful with this one, because notice it's not equal to the shape over here on the right, which tends to be the one that shows up quite a bit. So notice the equation y equals 0 is either, like, if you're just thinking about the xy plane, it is the x-axis. It's that yellow line drawn in there on the left. Or, thinking about it in 3-space, it's the plane, the xz plane. It is that left edge over there. So we're going from the x-axis up to y equals x squared. So yeah, this one tended to be a little bit tricky. I think most people ended up with this shape I drew in over on the right. Because honestly, like, I'm being honest about it, I think this one feels like it's more like it's the correct answer, even though it was incorrect on this one. This would be the bounds y is in between x squared and y equals 1. That y equals 1 being that rightmost plane, that right line over there. But that's not the bounds that are given. So I think that one just tended to be a little bit tricky when people were trying to repack this thing back together. So the shape on screen right now was the negative space of the region that we were describing. The correctly sketched region is the one over here on the left, the one that's back on screen now. Y equals 0, again, that's the x-axis. And then x goes from 0 to 1. Did I put the full thing on here? I did, yeah. So when we're switching our order to be x, then z, then y, the correct bounds for x are the square root of y up to 1, rather than 0 to the square root of y. I think that was one that tripped people up a fair bit. Yeah, I think a lot of people are getting 0 to the square root of y when we wanted the square root of y to 1. So careful on that one. What else did we have going on? Another one where I thought we should just look at some bounds. So we were supposed to be integrating a tetrahedron. And before I talk about this one in length, let me just talk about a better sketched version of that picture. So this is a picture that comes out of, this picture is in the notes for 15.7. But what we've got going on is if I plot my 3 points that are given, I have this tetrahedron, which is a 4-sided solid where each face is a triangle. And the tricky part to this one was trying to figure out the plane of this green face, the one that lies above the XY plane. And the reason why I think it ends up being a little bit tricky is because when we need to get the equation of that plane, we need the cross product of 2 vectors, but we cannot use the point that does not lie on that green plane. And that point is the blue one, the one that's 3, 0, 0, which otherwise looks like it would be the easiest one to use in a cross product, which tended to be a bit tricky. So I can't use that blue point because it doesn't lie in the plane in question. I'm going to need the cross product of the other 2 vectors. So if I'm looking at this picture here, it's the one that connects the purple point to the pink point, and the one that connects the purple point to the yellow point. Those are the 2 vectors that I want a cross product of. But if I back up to the one where I've actually got the work done out, wasn't the best picture because it's a little hard to see that face, because I just kept it the usual orientation for X, Y, and Z. But if we keep it that way, the face is just, it's a little harder to see what face we're talking about, which is why I just drew another picture where I've kind of rotated. What have I done here? I've sort of rotated the X and Y plane over a little bit so I can see on top of the shape a little better. So imagine I took the X, Y, Z axes as they were, kind of rotated them down and a little bit clockwise. So like rotating it down and clockwise so I can look on top of this tetrahedron, which involves a fair amount of multivariable thinking. But that's the shape that I wanted to be integrating over. So what that means is to find my Z bound, I'm going to want the equation of that plane, which again here looks like connecting some pieces. You need to connect some dots. So I wanted to connect the origin up to that pink point and the origin out to that yellow point, which here I've illustrated as a black and pink connection and a black and yellow connection. But it ends up being just the position of those 2 points, as it's pretty nice if we want to connect the origin to something. So our normal vector is going to be the cross product of those 2 vectors, which will get me gets me to a normal vector, in this case, negative 10, 5, 2. I can put that into the equation for a plane. I'm going to use the origin as one of the points that's in the plane because that's the easiest. Solve that equation for z, and I get 5x minus 5 over 2y. And then that is my upper z bound because I need that diagonal plane. So this one, I thought the conceptual part was much more interesting to talk about than the actual guts of the calculation. So I went ahead and I did it ahead of time. So we can just talk about the part about wanting to find the equation of that plane. Okay, and with that, that's the end of the material that I wanted to talk about. So I've been talking for a while now. At this point, I can tell my voice is starting to go. So I'm going to end the review here. So hopefully you're seeing this before you go and take the exam. So in that case, good luck when you take the exam. I believe in you. And I will see you again next week for the final exam review. Oh boy. All right. So unless I think of something else in the next like 5 minutes, this is the end of the review. So again, good luck on that exam.